world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic.
All right, hello and welcome everyone to Celestial Theodolite update number 32. Today we're going to be covering some new measurements at an old location. So Kat and I and Brian were able to return to the original location for the Getaway Mountain Peak that we took measurements on back in July last year. So on, what was it, December 31st, we got some measurements in the morning, so we'll go over those here in a second. But here's a quick recap of the original measurement. So here's the video. This is sped up, obviously, and then we'll watch the new stuff here in a minute. Now, enjoy this speed, boys, because this is the last time we'll see it look this good and smooth for a minute. But anyway, that was the original star there. And then Jesse was actually able to ID that for us. This is... he was able to reference the star, or the star that was up in the top right there with respect to this one. So he was able to ID that for us. But anyway, using the Peak Finder website, once you have the azimuth of the star that got occluded, you could just reference that with the observer coordinates when you go to the website here. So if you go into Peak Finder, you would enter, you would start clicking on these ridges here, and you would get your azimuth. And then once those line up, you know you're in good agreement there. So here's what the peak looks like in the daytime. We have some daytime footage of it here. Let me move that out of the way. So here's where we were at. We've got some pictures of it. Here's our field of view that we're able to get. So the original measurement was about right here. So that was the first one. So this is 261 degrees right here. And let's see here. So on the spreadsheet here, the ones that are not in green, the new ones that are added. So all these are new here. Anything that says unknown or that's not in green, it hasn't been verified exactly yet. So there's still other stuff to go over. I just haven't got around to IDing everything. I have to actually go back and when it's nice out during the day and take C-star footage of the ridge itself to get where some of these occlusions are at. But let's see here. We'll go over the ones that are verified though. And I'll have the data and recordings and stuff. I'll forward it in the live chat here in a second so they can be, so everyone can, you know, go over them themselves and stuff. Give me 1 second. I'll put that out. Let's see. Here. There we go. Forward. Live stream text chat. All right. There we go. In the live stream text chat there, and I'll pin that. There's all the necessary information. Now, if you download the files from Discord, it'll actually change the file name, so you won't have the correct epoch. You'll want to either reference the Obsidian link there and the zip files, or the zip, because it has the original time on there. So that's important for you if you're going to, if you don't trust the occlusion times or the conversion or whatever, if you want to do it yourself, you would need to start with the correct epoch. So you would want to download the zip file for that. Let's see here. So anyway, we'll go over these now. So this is the mountain peak over here. So this is Getaway Mountain at 261. We got some confirmed occlusions over here at around the 250, what was it? I think it was 254, 255-ish, 254 range. So right around here, right in this area. All right, so go ahead and play that now. Stay here. Why is this not? Oh, it's back here. Let's move you to. There. Okay. Anyway, sorry about that. So we see here there's 3 stars visible, and with this and with this pattern here, it made it very easy to identify. So it was a partially cloudy night, and we were running into a scenario where the stars were getting, low in the horizon there, and then they would uh, they would go extinct before they actually got occluded by the mountain. So I was readjusting the C star, and it doesn't tell you it's azimuth or whatever. So uh, just going by off of what we could ID off of star patterns, for sure at locations, we started with these ones. So we have these 3 stars here, which come out to be Beta Catos, X set, and then this other one, Easy set here. So let me turn off the terrain. Okay. So I have the outline frame of the C star here. This is 44 arc minutes wide and 77 arc minutes in height. And then there's an import that you can do from the website that I was using earlier, the Peak Finder website. You can import the silhouettes. Now it's not an exact one-to-one match or anything, but it's a nice visual overlay to kind of show you what you're working with. And it did incorrectly import the names and stuff, so it's not 100% on that, because it doesn't even have getaway here. This should be getaway, but it's not. But anyway, at this azimuth here, 254, that's our matching azimuth. So we started with these 3 here, and then a couple minutes later, the star here, 53 set was occluded, and then later we readjusted and got this one as well at about this location or so. It comes out to be like 55 arc minutes instead of 54, or I'm sorry, it comes out to be 255 degrees in azimuth instead of the 254 like these ones down here. So it comes out to about right here. But anyway, we'll watch the occlusion now real quick. And by real quick, I mean painstakingly slow, while building the anticipation of these as these stars inch towards the mountain. Enjoy, lads. Enjoy.
I'm tripping. I can't really tell if it's moving.
It's moving ever so gently. So this is 1 frame per second, and this is like basically what they look like when they move in the sky when you're looking at them this close. But yeah, anyway, we'll continue on here. We're about to hit our mark. Now here at 152, you can see it's just now at the peak. And then at 55, it's gone. So I put that down as, I want to make sure I did that right. Easy. Did that not update? Why did you not update?
Yo, was that playing in real time, or what was like the?
Yeah.
So 1 frame per second.
Yep.
Oh, so that was real time.
Yep. Easy set.
That's crazy.
What did I get for that? 155. Yep. So yeah, what you do, you take the epoch here, convert this into hours, minutes, and seconds, and then since the frames are 1 frame per second, 1 second in the video is just adding 1 second of time to the original epoch when the video was started, and then that gives you the occlusion time. So 1:11:53 was the occlusion time, and then a couple minutes later here we get this one here at 1:12. So now 216 here, you see it's just barely above the peak, and it's not really like setting into the peak or anything like that. It's staying at that ridge line as the barrier, and then it's being slowly covered up there, and then now it's gone. So that's when we take the metric for when it's 1 second after it's no longer visible. That's when we take the clock for the occlusion time there. So 222 is what I have on the thing. And then I let this play for a couple seconds. Oh no, and then I readjusted to get this star, which was the Baton Katos one. So we'll go ahead and watch that one real quick. This one was really cool because it's a pretty big star. Probably the biggest one that we've had occluded. So we get to see the mechanics of how it gets occluded here.
Just out of curiosity, how far away is that star right there?
Ground position, relative to us, you mean? Or do you mean?
No, it's not really relevant, I guess. Just the amount of light years. Just curiosity.
Yeah, super not relevant.
Yeah.
All right, but now I'm
It's pretty close. That's all I'm getting at.
Yeah, I feel you. It's I think its distance on here is somewhere on Stellarium. The parallax. I think the parallax will probably tell you its distance. So if you convert that from angle into distance right there, that should tell you.
I think it's up like four lines from where you were.
Oh, is it the actual thing? Oh, distance, yeah, 253.23 plus or minus 4.13 light years. Yeah. Woo. Plus or minus 4.3 light years. All right. So we'll continue on here.
Thank you for that, whoever asked that question.
Yeah, I'm glad you asked it now. Forgot about that aspect of it. All right, boys, get ready. It's coming. I'm gonna mute you, Selviz, because you're driving, but drive safe, brother. We can hear your turn signal going off though. Pull over if you're gonna watch the occlusion.
I'm just glad it wasn't me this time.
Oh, welcome. Jason Bourne is here to join us. For those of you who don't know, D3 woke up with latitude and longitude coordinates tattooed on his back, and he's been trying to figure out the meaning of the graticule ever since.
The map led me here, man.
All right, here we go to the occlusion. Now, in this case, it did kind of look like it was setting into the peak, but you can see right here, there's a little, it actually set in this little pocket. So as soon as it got to that pocket, that's when it started becoming occluded. Very, very cool. All right, so I added the numbers here to the spreadsheet. Now I got my distance from using the latitude and longitude coordinates and just haversigning. So in the data table now, all the distances should be computed. Nope, that's not right. Or wait, no, I didn't change it for everything. Just a couple of things. Okay. Well, anyway, in the future, everything is going to be changed to just use haversign to derive the distance based off of the latitude and longitude coordinates. So none of these distances will change, but that's just because we already did that, but I'm just changing it in the thing to have it come from here instead of being an input. Anyway, using the coordinates given here in our starting observer coordinates, when you click on this, you can click here and it gives you the coordinates of the elevation that you're clicking on. And in Google, this actually you can enable the USGS topographic settings here. So this is the location we were at. If you put it on Google Maps and look, or Google Earth and look, this is the bearing for the azimuth of those stars that were occluded. And remember that first one was right here. The original was the original one. No. Nope, that's not it. Yeah. So the original one was right here, 261. And then this is our 254 here. So this is about where we were looking. Anyway, what you can do here is get in the USGS topographical map there, head over to those coordinates that were given, which was, oh, I didn't input them, did I? Yeah, I did. So if we come over here, oh, that's just the line to it. That's not it. Frick. How did I not do that? Well, one second. I'll just grab them from the website. All right. So using the latitude longi there, that's where they're saying it got occluded thereabouts. But the actual heading or whatever comes out to be right here for the ASI. And then we can see that elevation that it comes out to when we check elevation profile. We can see that it corresponds to what they were saying for, what did we have for that? Is that 54? Why 54? What star was this? This one. 54, 43. So 54, 43 would be right around here at the 2000 meter ish mark. Yeah. Get that 3. So anyway, when we reference, this website, and then we reference the USGS surveying thing or overlay and the elevation given from Google, we can see that they're all in good agreement there. And the reason I brought that up specifically is because remember in previous weeks, we've been talking about central angle theorem and how the central angles line up on these for all the measurements. So before we come back to this, let's take a refresher on Pikes Peak. So Pikes Peak here, angle equals distance in the spherical coordinate system. So 27 arc minutes is actually 50,551 meters if you were to convert that relative to the center of Earth through the conversion. And anyway, you can divide the distance by the radius of Earth to get the arc minute there conversion. So for 27 arc minutes, if the star's ground position changes by 50,000 meters, or I'm sorry, 50,551 meters, then it's going to drop angularly relative to the observer by that same amount. So coincidentally, we can reference a mountain peak at the end of that angular descent, and we can see, we can compare the true positions based on the occlusion timing to see where they're lining up geometrically for the observer to get the occlusion. But anyway, with that, what we can do is we could subtract the star's true position at the time of occlusion from the true position relative to the observer, and we get the 27 arc minutes, which is exactly what it should be for the central angle. And then over here, actually, that's just referencing them. That's just exactly what it is, what I told you. So, and then this is just another way to do the same thing, but primarily we want to make sure that this number here matches this number here on F17. Super important. So it's pretty close here. It's only off by arc seconds, which is pretty, acceptable. But when we look, so now we're going to look at some deviations here and see what like the minimum maximums are on what we get. Cause we got, the ones on Getaway Mountain / Patikatama or whatever, however you pronounce that, are, Potempi. Anyway, however you pronounce that, are the greatest air so far that we had in that. So if we look at Blajat Peak here, it's off by 0.07 arc seconds. That's like not even an actual difference. That's like super spot on for that difference there. And then for Cheyenne, 4.4 arc seconds off, still looking good. Blue Mountain, 0.1 arc second. Let's see, Rosa, spot on, couldn't be any closer. Green Mountain, 0.08, very nice, looking clean. North Peak, we get 27 arc seconds. Let's see, and then for this one, same location, just different star, we get 0.37 arc seconds. And same location, different star, 10 arc seconds. So let's see here. We go to Getaway Mountain. This is the original star that we first watched at the beginning. There's a 10 arc second deviation here in the star drop at the time of occlusion. Houndstooth, pretty much spot on, 0.21 arc seconds. Not even a real difference. Let's see here, where are we at? Old Blend. So we got 2 arc seconds here for Old Blend, and then 11 arc seconds here. Same location, different star, and then same location, different distance, different stars. But Mount Blend again, 26 arc minutes for difference, and 0.00 or 0.09 arc seconds difference. And then this is Goose up in Canada A, 0.08 arc second difference. Now we get to ours. Now we just watched the video. We know where they got occluded. We have their azimuth and all that. Now for here, we have 3 arc minutes in difference. So these did not correspond, like the full angular drop isn't being represented here. And I'm not sure why yet, but this is the highest deviation we've seen in the central angle check so far. And now the thing that would make this inaccurate, or like that would change this, is like the distance would be wrong. But referencing the elevations given in Google, at the time of occlusion and all that, I don't see how the distance is actually wrong or whatever. So anyway, if anyone has any ideas, thoughts, or comments. And here's the other mountain here. We have, the other star, pretty much the same location. It was at the same time.
I have a question.
Yep, go ahead.
Once the star is occluded, let's say 2 seconds after it's been occluded, does it have a GP?
Yeah.
Rest my case.
Yeah. So in the internally consistent coordinate system that we're all referencing here and using, yes. No one's disputing that. That's our premise. I'm glad that you are caught up, my good sir. Actually, we have the ground position actually not on these ones yet, but we have the ground position relative to the observer, within the coordinate system on a few of these here.
Yeah.
It's not an issue.
Yes,
It's like
ma'am.
resting your case on that is kind of a weird thing. All right, you're hot, Mike and Beast.
Yeah.
But anyway,
Sorry.
you're good. We got 3 arc minutes here off on that one. And then on the one Baton Katos here, this one came out to be 1 arc minute and 50 arc seconds, which is basically 2 arc minutes. And that's where we're at so far. We still got, let's see. We still got 7 other videos to go over and verify. So we'll be working on that. And then we have, let's see. What I plan to do is take an image like this and then like reconstruct it from the perspective of the sea star as we pan through frame by frame, and then have like a nice panoramic of the whole ridge where we have all the occlusions, and then have them all marked out with their azimuths and all that displayed so that it looks all nice and easy to understand or whatever. Are there any other questions?
All my questions are have to do with the eclipse stuff.
Well, I think Brian's here if you want to ask him.
All right. Well, maybe we'll wait, see if anybody has any questions about what you presented.
Cool. All right. But yeah, so while we went over the central angle deviations. Let's look at the predictions for flat Earth, globe Earth. So here we are 12 arc minutes off at the time of occlusion, which gives us what is it? Puts us 85 meters off of the peak. No, 185. Or 182. 182 meters in difference. And then for the globe, using the observer centric position there for the true position reference, they're off by 366. We're off by 182. If you subtract these two, again, they do come out to be the half gamma representation. So like that part is still, actually, no, that would have to be off too, wouldn't they? Hang on. Let's see. What am I doing? Minus. Yeah. When is F12? Oh. 20. So yeah, it's 3 arc minutes off. There's the 2 arc minutes. Now we have to convert it. Now I have to know. Six arc minutes. What? Yeah. Yeah, so it's 2 arc. Yeah, it's 2 off of the central angle there. But yeah, globe's still sharing the majority of the air of the central angle that we could come up with there. And let's see, this for Baton. Easy set. Mm. Mm. All right, so 20 or 12 off for flat Earth and 23 off for the globe. And the interesting thing about this location too is the refraction correction. So they have the same refraction correction amount this time of year as there was 7 months ago. So if we go to Getaway, same location, just different ASI, they're saying 23 arc minutes of refraction in July at this angle. And then later in the year, 6 months later, 22 arc minutes of refraction. And then time of occlusion puts them almost 2 arc minutes above the peak for the refracted position. Yeah, so let's see, another almost 2 arc, yeah, 1.42 there, almost 2 arc minutes above, and then probably the same for this one. Yeah, same exact for that one. So being above the peak at the time of occlusion geometrically for the refracted position. All right. So if there's no questions, and if you wanted to ask Brian about the eclipse stuff, you should be free to go.
All right, sweet. So I did a write-up, a more formal write-up. I'll link it, and you guys can go over this.
Awesome.
But my first question is, which I've asked before, is like, why do you guys not use the celestial theodolite method for eclipses?
So the biggest difference between the eclipse and the mountain star setting is you basically have to find what the angle is, the occlusion angle for an observer on the moon, and that's not really possible. So I just did the best that I could with the data available.
Well, I mean, you could just use a library. Stellarium, just like all the stuff in Stellarium, when you do it from the mountain, is just based on like an astronomy library.
But we don't even know what the moon is or what the height is or any of that, so you can't.
I mean, you could guess a height. You could guess a height, and then you could plug it in and see if it matches the like flat Earth trig.
Stellarium predicts the angle, it doesn't predict the distance from the Earth. It just maps it to the celestial sphere, which is a fixed sphere radius.
I don't think that's totally true. I think most modern astronomy libraries, they use like actual like positions. It'll correctly track like parallax, for example.
Stellarium uses
that is true for the moon, but it's not true for the sun.
It is true for the sun.
Stellarium uses a ephemeris developed by JPL. It's a bit dated, but it predicts the positions in 3 dimensions for all objects within the solar system.
That's totally not true because you cannot set your altitude higher than 60,000 meters.
Have you looked at the code? Because I have.
Have you tried adjusting your altitude though? Because when you do, it doesn't make a difference when you go to different altitudes. So that's the issue that he ran into.
What do you mean
Yeah.
by?
So one of the things that I did is you can just go use a third party library. It does the same thing that Stellarium does. There's ones that are even better that don't have the same limitation.
So if you're talking about changing your altitude 60,000 feet, meters, or what have you, and then the distance it reports to the moon is not changed, is that what the issue is?
No, it's different. They basically want to take the altitude angle from the moon to the sun.
Okay.
Because that's the celestial theodolite method. So
Okay.
my point is you could get a library and you could do that. I did that.
That assumes the height of the sun, and that's what you're solving for. So I don't know.
I know, but the whole thing, like the whole point of this is that you guys say it's internally consistent.
Yeah. So, and if you're starting with the height of the sun, you're not solving for it, which is the purposes of what he was doing, to independently derive it. And what he independently derived was consistent with the celestial sphere model, using the 6210 at as an altitude essentially.
Yeah, but I'm not talking about solving for the height of the sun. I'm talking about solving, like doing celestial theodolite, where you get the angle and then you just see does that match planar trig?
Yeah, and what you're describing, as you just said, is impossible to do without first assuming one of the other variables that we're trying to derive independently.
No, okay. So let's say we don't know the height of the moon, but you have this system that you guys say is internally consistent. So just like guess, you guys could say, all right, we think it's at 6,000 feet or 6,000 kilometers. Hold on. You could say it's at 6,000 kilometers, and then you could plug that in and say, okay, now what angle do I get back? And does that match planar trig? And then you could move you could move it up and down. You could basically just do like a fitting algorithm and see at what point, what height you have to put the moon at to get it to match planar trig. I did that. And you have to put the moon at 400,000 kilometers, and then it works for planar trig.
Brian, didn't you do the same thing?
Well, so all I'm solving for is the ratio of moon to sun height. So there's just too many variables. You couldn't possibly do that.
No, what I would say is not as...
No, but Brian, didn't you just derive it off the angular drop relationship?
Angular drop relationship.
Yeah, and then just use tangent functions. Look right here.
Yeah.
Like he's saying like plain trig to get it to match and all this, like as if you didn't do that specifically.
Well, no, you did that. You did that after sort of coming up with a made up height of the moon. What I'm saying is like, why go through all that? Like, just follow the method you guys set out.
Because we're trying to derive it independently, and you can't do it without first referencing already known factors to get the positions for what you need.
So I made a guess for the moon height, and it turned out to be consistent. But you can't also guess the sun height. You're trying to solve for the sun height.
It defeats the purpose. You're trying to accomplish a different goal.
Well, I'm trying to it's the celestial theodolite method is wait till an occlusion happens, go to the point of the occlusion, and since stellarium's internally consistent, we use stellarium, or like in other places you've said use a astronomical almanac, which we could use. So use that. It's internally consistent, so use that and see if it matches planar trig. But you guys didn't do that. You guys completely abandoned the method.
No,
and then you did a different method, which I think also has problems. But my first point is, it's crazy that you guys abandoned the method.
When this was introduced, it's introduced as a new application of what we already do. This isn't the celestial theodolite method or abandoning it. So like you're trying to merge it with two different things and then also say that it doesn't work with the way that you did it. It's like you're doing a different goal. That's it.
It's not a different goal. It's the same. It's the same. Like we know at a point of an occlusion, according to you guys, we have a straight line between the two. And we know that according to you guys, stellarium's internally consistent. So I just followed that through, got a result.
Agreed.
But the result is, as you guys know, I'm sure that anytime you do this for an eclipse, the angle you're going to get from the sun to the moon is going to be like almost straight overhead.
Yeah. So if you derive it using just the angular drop and referencing that for the internal consistency, you get the altitude of the celestial sphere, which happens to be the 6210 thing. So that's all that's being referenced. Like you're doing a completely different thing. And then saying it doesn't, and then you're saying it doesn't work after I already assumed XYZ variables to start my triangle. Like that's,
I'm not assuming any variables, and you could pick any height of the moon to do it. I don't feel like I'm straw manning. I feel like I'm following the celestial theodolite method, the one we're using for mountains, and I'm just applying it to eclipses. And I did a write up.
How can you calculate the angle from the moon to the sun without knowing the sun's height?
Use stellarium. That's how can you get the angle to a star? How can you get an angle to a star from a mountain if you don't know how far away or how high the star is?
What I'm hearing is the celestial theodolite works independently, and so does the eclipse thing. So you're going to merge pieces of both to make a new thing, and then try to argue against that. Is that what your write up is about? That we're going to read?
I'm trying to. No, the first. So my write up, the first half of it is that you guys don't actually follow your method. That's what I'm pushing on.
That's the premise when he opens up and says this is a new application and goes over the issues of solving things by assuming the values there. So this is an independently derived method. This isn't referencing anything. One second. This isn't referencing anything other than the angular drop over distance for the position of the moon to get the elevation, like to get the physical height as an elevation, not the angular elevation. So what you're doing, again, different thing, different goal, merging the two, and then saying it doesn't work.
Okay, we can move on from
the sun, and we know the sun is closer than the stars because of the way that they occult one another. The moon occults the sun during eclipses. The moon occults the stars. The sun occults the stars when it rises.
You're not saying anything that's in contention.
Well, you're treating them all in what I don't know. Seems like
I know you don't. I know you don't know. That's why you said something that's not relevant that no one was talking about.
All right, so we can move off this point to the next one. I would just say even in celestial theodolite for the mountains, you guys don't ever know the height of the star. You don't claim to know the height of the star. You haven't tried to calculate the height of the star. All you're doing is saying, give me the angle from the mountain to that star, and then you're using that to do planar trig. That's what I'm doing. I'm not doing a different thing. If I am, you can point it out. I'm not trying to straw man it. I'm just saying if you follow your method to a T, it doesn't work. So we can move on.
But whatever, that's cool. It's cool you wasted 4 weeks on that, though. I can't wait to read it.
Well, no, it's cool. I told you that we could do a thing on it. So if you want to go through, and how long do you think it'll take to bang this out? If you want to do it as like a Prezi right now, or do you want to do like a formal one next week or something?
No, that's fine. I mean, I think the first point about the not using the method, that's probably like a third of it. Are you saying you don't want to go over it right now?
No, I'm saying I'm saying finish your, go ahead and go through this. Knock it out.
All right, yeah. Okay, so the second point is, so like scrap all that. Like you guys didn't do the occlusion stellarium thing. Basically, I'll try to explain it. You can tell me if I got it right or wrong. But what happened, what you guys did is you took the central angle points, so got them from NASA. So this is like, not the central angle points. What do you call it? Basically the center path of the shadow from NASA. So there's a bunch of long points that represent the middle of the shadow. Yeah, there's another, I can't remember the word for it, but anyway, yeah, the center of that. And then from each of those data points, you took that point and you sort of walked it towards the GP of the moon. And you did that in like 69-mile increments.
Yep.
Measured the stellarium apparent height to the moon from each of those locations. and that gave you, and then basically you did a plot fitment for that data set. Is that correct?
Seems to be.
Okay. And then you took that, and basically there was a big leap in there, which I didn't go through this in my write up, but it was sort of like the moon came out to be a little bit lower than the sun. So the sun was going to come out to be essentially the radius of the Earth. The moon came out to be about 1.5% lower.
Something like that, yeah.
Yeah. And so then those two heights essentially became the basis for what you guys did the planar trig from. And the method, if I believe I understood it, the method said, okay, during the eclipse, we have, like the sun and the moon are swinging. You got different like azimuth angles. You have the GPs are spreading apart or whatever. Because of that, we should see, if we go back and do planar trig, we should see like this wild difference when we calculate the height of the sun. And because we don't see that difference, that is a sign that Earth is flat.
Question. So again, when you talk about the height of the sun, you're talking about an angle, or are you talking about an actual linear distance?
So linear distance in this case, the purpose was to associate a linear distance to the angular altitude.
Okay. So what is your contention as to whether or not the height to the sun is constant over all time?
That was what I was solving for. I was checking to see if it is constant or not.
Okay. Because I have
that
angular.
was like the test. That was the test, and it was like if we see a consistent result and we didn't account for Earth curve, then that shows that the Earth is flat.
Okay. I'm just saying that I have.
Yeah, presumably the Earth curve would have shown up in the elevation differences when calculating it out, right, Brian? Is that more or less the premise?
With a local sun, yes.
So maybe I'm not. So I have data about the angular size of the sun, and it clearly indicates that the angular size of the sun changes as over the course of the calendar year. Now, the reason for that, as the heliocentric model, as it were, would tell you, is that the distance to the sun from the Earth is changing over the calendar year. So I'm wondering whether or not, are you looking into that, or are you considering that at all?
The change in the angular size itself is not currently in any sort of contention that I'm aware of.
What I'm asking though is, according to the globe model, if you will, the angular size of the sun changes because the distance to the sun, which you are trying to determine, changes as a function of calendar year. So I'm wondering if you are trying to find that, if you are trying to account for that in any way. Like, are you assuming that it's going to stay the same?
So all the data I had was over a 112-minute window. So I was assuming it was constant over that window because the change would be negligible. I don't have data outside that parameter.
Oh, okay. All right. I didn't know if you were taking, like with the other celestial theodolite data that I've seen, it's been taking over a span of several weeks, I guess. So I didn't know where you guys were with this part of the experiment.
Yeah. So my question would be like, how would you like falsify that premise, saying that we expect to see this massive error?
Good question.
I don't know what you mean by falsify.
So Brian plotted out the elevation differences for what it would be on a globe for the path length of the shadow. So I think that's the comparison we're looking at right here. Is that correct, Brian?
That is apparent versus what I'm calling the actual position.
And the actual position is the altitude that you calculated earlier based off of the angular change of the sun with respect to nautical miles?
Correct.
Okay. So if the Earth were a globe, it would have followed this altitude trend because that's what the 60 nautical miles per degree angular descent would look like over that distance.
That would be if the sun was where we see it to be.
Oh, so like using the apparent position is the apparent position's angular descent, rather.
Yeah.
Yeah, but this is
Gotcha.
the apparent position because you have apparent with refraction, you have apparent with
right. Yeah, it's not
like stellarium's always apparent,
Hmm.
and then there's another true altitude that we never see and nobody knows.
So when I say apparent, I'm just talking about the effects of how we see, sort of like perspective. There's no refraction involved.
Right. That's kind of my point. I think in the other celestial theodolite, apparent is used to describe like a stellarium angle with refraction.
Yeah, I should have chosen better terms to be consistent with Alan.
Yeah. So I did a couple things. So I challenged the premise. I'm curious if you guys have an answer for it. So the question is, like, how do you know that there should be an error? How do you know that there's not already that the data set itself doesn't have a prefixed in ratio that you're
so if this isn't representing
it has nothing to do with that.
Right. What I'm saying is if this isn't representing true to true, we would need to have another one to simulate what it would be like for the elevation change for the globe to see it accurately. That would help. Do you agree?
Yeah, I mean, it would help. Yeah, basically, you could predict like what you should see if it was a globe.
Yeah, correct. We should definitely implement that. I agree. If that's
like because what I think what you'll find is that it doesn't the eclipses already force a constraint, and the constraint then makes it where all the algebra for it works out. I'll link in here. I did a GeoGebra to kind of show. I don't know if that's how you say it, but this will show it's essentially just a sun moon. It's circular. It's not 3D. It's only 2D, but it shows that in this case the moon travels a little bit faster than the sun, just to try to get some of that aspect of it. But you see, basically, I can make these things go in a circle.
Oh, can you send the link again? It didn't. I don't see it. Or the GeoGebra link didn't.
Yeah,
it's just like a regular. It's just the regular GeoGebra calculator link.
Oh.
You want me to build it myself? Give me 1 second. Just kidding.
All right, yeah, sorry, that's my bad. Here we go.
Oh, sorry, I didn't.
The other thing I did,
part.
which sort of got me thinking, the other thing I did that got me thinking on this method of like looking at this is I just went in the spreadsheet you guys have where you have you put your moon height in, you did all the calculations, and then you have like the error amount for it, and I just changed the moon height to like 1,000 feet or to 400,000 feet or 400,000 kilometers, and it doesn't matter. You can set the moon to any height you want, and you get the same consistency.
Yeah, so all I was solving for was the ratio of the moon's height to the sun's height, but the thing that's important is just it's flat no matter what you pick.
Right. Okay. And so I figured there's like I was trying to attack it from both angles. One is that it doesn't like I think they were sort of like, oh look, we calculated the height of the moon to be this, and then when we plug that height of the moon in, we get this really consistent sun result. So I just want to be clear. It doesn't like you can put in a height for the moon of 400,000 kilometers and you still get a consistent result.
Yeah, my height for the moon was just a guess based on how it curved in stellarium.
Okay, and then the GeoGebra part of it is just to show that the eclipse already fixes these ratios fixes it just in by nature of what it is. It's not true that you could take any 3 like sun, moon, earth alignment positions and get a consistent result, but you can for eclipses. So I think what you did is you just found a relationship that was already there and assumed that validated your approach. So what I would do is I'd work on falsifying and showing how a globe would actually make that result, get it to break, I guess. Okay, and I have one more point, sort of 1.5 more points. So the first one is, or the next one is the, you did the tangency for the moon. So there's this, here, I'll paste it. So what you did is you took the, this angle that you got at the very beginning when you did this, I don't know what you call it, but walking along the shadow center path, and then calculating walking towards the moon and calculating the altitude angle. And then you took that angle, you converted that to a central angle. You got 88.7, and then I just pasted it in chat, but then you essentially set up a right triangle and then tried to calculate the distance to the moon. Can you guys see that?
Yes, sir. It's up on the screen.
Oh, your screen up right now. Okay, so the problem with this, and I think it was my first thought when I saw this 88.7, like a lot of globers were trying to figure out, okay, where does that come from? And it basically comes from parallax. So when you're looking at something, I'm talking about like a topocentric angle, you're on top of the Earth, you're looking straight up at something at the GP. Your parallax is 0. As that goes down towards the horizon, you're going to introduce parallax, and the parallax will be more the lower the object is in the sky. So this is why moon has, I don't want to say a lot of parallax, but there's a much more noticeable amount of parallax than there is with the sun. So that's why you got a different answer. That's why you got the 88.7 for the moon, and you got something a little bit higher for the sun. And the problem is you can't, it's kind of like one of those, you can't do that sort of things.
You can't do what?
You can't take topocentric angles to the moon and then convert them to central angles, which is basically what you're doing here. And the reason is that the further away you get from the GP, the topocentric altitude angle is basically gonna shrink faster than the central angle. So I'll post a graphic here for that.
Is this true, Brian? Were you doing something illegal with the triangle? What the ruck?
Okay, so this shows you so you can see basically the angle C and the angle O. So the O is the topocentric. You can see in this picture pretty clearly the angle, that O angle is quite a bit smaller than the C angle. So this is an more extreme version. The moon has, you can calculate the max amount of parallax from like the distances or whatever. So what I did is I just picked a random time and just went into Stellarium and got the actual moon GP. And then I went to like where the moon was right on the horizon. And you'll get the correct central angle, which is going to be closer to, 80, I think right around 89. And so then if you do the math on that, you'll get 354,000. That's what I got, 354,000 kilometers. And then I think my half point is the same sort of thing with the sun. So there was another diagram you did where you showed that you referenced that you'd written a Python script where the angles didn't match up for the sun and moon. I didn't have the Python script, so I couldn't really speak to it. But you're going to have basically the same problem there, because what you're doing is you're trying to create a triangle using a central angle and then using a topocentric angle. That's another one of those, like, you can't, like, they're not, it's you're trying to combine apples and oranges into a triangle. So if you do it correctly, and then you basically readjust the topocentric angle, then you can make the angles work out.
That sounds reasonable.
All right, that's it for me.
All right. Brian, did you want to respond to any of that?
No, I don't have anything to say.
Well, I'm curious myself about his point on the topocentric versus the central. Does that a factor that should be considered? Because it sounds,
I'm not entirely sure what he's saying, so I'd have to look into it.
So he's basically saying that from here you're using the central angle to establish the intersection for the moon, for the what is that? The hypotenuse of the triangle.
Oh, okay. I see what you're saying. Yeah.
Yeah, and then so from here on the top, he's saying it would be slightly different, and if you do it from the top eccentric angle, you'll get the correct. You won't get that excess that you got. That breaks it. So he's
Yeah, I think
basically
it's
saying,
inadvertent. I think what happened is like as you walk towards the moon, basically wherever the point you started had the most parallax. As you walk towards the moon in that first step, you're going to decrease the amount of parallax. So it's not like you're not getting the full parallax at 90 degrees, but you're going to get some amount of it encoded based on how far those data points, how far the eclipse shadow is from the moon, basically. My guess too is I didn't do this, but if you graphed out the plot points based on how far away they are from the moon, my guess is you're going to see that angle. Like instead of getting a fitment of 88.7 degrees, you're going to see that be much lower on the first side of that calculation, and then at the end it'll be pretty much 90 degrees.
all right, well, I do agree about what you brought up here with that. That makes sense to me. So but yeah, thank you. And we'll take a further look at what you wrote up here. Did you have anything else to go off of that?
No, I think that's it.
All right. Well, we will go over this and get back to you in a formal write-up as well. Thank you very much. All right. Are there any other questions, comments, or concerns tonight regarding the regular Theo method itself or the Eclipse stuff or anything like that? If not, we'll probably wrap up here in the next couple of minutes. All right, I'll take everyone's silence from those who are invited to participate in the Celestial Theodolite, as that there are no further questions. So we'll go ahead and wrap up. All right, I'll be right back, lads. All right, let's check in on the chat here. See what the lads and ladettes are up to. Hello and welcome, everyone. Bredimus, Shalom, Rod Silva, Ion, Space Later, Cat, Nominal, JT, and my boy Schmidt. Shout out to the boys. All right, we're wrapping up for the night. We'll see you guys. Tony Coriolis, there he is. I see you out there in the streets, young Coriolis. All right. We'll be back on Tuesday for a reading night, for an Ether Cosmology Roundtable reading night. Be very exciting. We're going to be reading a modern review of the old Mickelson and Morley. So tune into that tomorrow night at 8 p.m. Eastern, 6 p.m. Mountain, and 5 p.m. Pacific. Then we'll be back again on Friday for the Friday community Twitter space. And that'll be around 8 p.m. Eastern, same time as always. Actually, everything's pretty much always 8 p.m. Eastern if I can help it. So you can work backwards from there to your respective time zone. But see you guys.